All right. Hello, everyone. We're here to, I hope you're here to see a talk about Kubernetes and Akka. And I made the title of this talk, The Beginning of a Beautiful Relationship. And it really is. But before we get into that, my name is Hugh McKee. I'm a developer advocate at a company called Lightbend. And you may have heard of some of the things we do. The most famous, I think, in many cases for us developers is we're the company behind Scala, the Scala programming language. One of our co-founders is the creator of Scala. In fact, just a couple weeks ago, we had Scala Days in Lausanne and celebrate the 10th anniversary of Scala. And we also have a couple other open source frameworks called Play, which is a web framework, and Lagom, which is a microservice framework. But really I'm here to focus on the thing I love the most about what we do at Lightbend, which is Akka, and Akka actors in particular. And how many of you guys are familiar with Akka? Okay, pretty good amount. How many I usually ask, I run into people that are doing Akka, and I say, oh yeah, cool, you're doing Akka, are you using Akka clusters? And that's where it kind of trails off. So a lot of people start using Akka because they're interested in perhaps in Akka streams, which is a feature of Akka. But in Akka actors, the actor system can span multiple machines, so it can run in a cluster. So Akka is also 10 years old this year, by the way. So it's been very, very active. We have engineers at Lightbend that are the stewards and the primary developers of Akka, which is of course open source. And there's many developers that are contributors out there that are also helping to evolve Akka. So it's pretty battle hardened at this point. But one of the really interesting features, and this is really what drew me to Akka in the first place, was Akka clusters. But the big thing that was really missing with Akka clusters was an orchestration layer. So Akka is great at handling things kind of at the actor level, handling things that are running inside JVMs, running in a cluster, but it didn't have anything to handle running the JVMs. And then Kubernetes came along, and it's like the heaven's gate opened up for us, because this was a beautiful orchestration layer for us to run a cluster in. So that's really what I want to talk about, is this kind of, in my mind, there's this love relationship of, Kubernetes could care less about Akka, but Akka really loves Kubernetes. So just to start, when we'll look at Akka and Kubernetes in this talk, but I wanted to walk you through, I think which is a really good definition of the actor model, which has been around since the 70s. It's like the first paragraph on the Wikipedia page. And it really, I thought it was just succinctly and precisely summed up what actors do in an actor model. So the actor model is really a model of concurrent computation. And we'll see what that means in a little bit. But it's a universal primitive of computation. So it's kind of like a building block. In this picture, I've got a Lego block, Lego blocks. And so with Lego blocks, you can, they're very simple. They have very simple mechanics. They plug together in whatever ways. But just like with Legos, you can do simple things, but you can do really awesome things with Legos. And it's the same thing with actors. With actor systems, and especially actor systems running in a cluster, you can do some really elegant, powerful things with systems of actors. It's a different way of thinking about building systems, but I know for me, once I wrapped my head around the concept of an actor and how to use an actor and things like that, I just all of a sudden, things started to click, and I was amazed at the kinds of things that we could do. So with an actor, the only way to talk to an actor is you send in a message. And the analogy I always use is, it's like you and I texting. I send you a message. That's really an asynchronous message. Now, how you respond to that message is up to you. I have no control over that. I'm just sending you a message. And I can continue on doing whatever I want to do. I'm not frozen, suspended, waiting for a response back. I may be expecting a response back, but that's the behavior that I built into myself. And how you respond to that message is things like, when you get a message or an actor gets a message, the actor makes a local decision. And some of those decisions could be, well, the actor could create more actors. and then that actor could send messages to those other actors. And this is kind of a form of delegation. It's like, I asked you to do something by sending you a message. You create some workers for yourself, and you send messages to each of those workers, and they're all running in parallel, maybe doing tasks on your behalf. So you basically delegated work. So say I get a message from somebody, and then I send messages to you, and and say, can you do this, task A, B, C, D. And then when you're done, say our deal is you're going to send me a message back. Something like that, but it's a form of delegation. A really cool feature, though, is, and this is fundamental to the way actors work, and it's one that's not used enough, I think, in Akka, which is actors can be change the way they'll respond to the next message. So a simple example is, say there's an actor that's in a state, and say it's an idle state. It's just not doing anything, whatever that might mean for this particular actor. And then that actor gets a message and say, can you do this task for me? So that actor switches into an active state. So if somebody else sends the message, hey, can you do this work for me? Now the response message back from say, for me, when I switch from an idle state to an active state, is I send a message back saying, sorry, I'm busy, I'm doing something else. So it's this behavioral change that is quite powerful in the way actors work. And this is fundamental to the actor model, but it's implemented in Akka, the way things work. And in fact, Akka typed is just coming out, which is a new way, it's a more strongly typed way of messaging between actors. But one of the really nice features of Akka typed is that the actor is always responding with a behavior. What is the way I'm going to respond to messages from this point forward? The other thing is actors are stateful. So actors maintain their own state. And the only way to change that state is for actors to get a message and the actor decides how to change his state, which is really pretty powerful. And this is a feature that people often use when they're using Akka for concurrency, is that this is a very nice alternative to do multi-threading, where you're not dealing with semaphores and locks and things like that, because it's just kind of a natural way in the ways actors interact with each other. So anyways, I thought this was a really nice, quick, concise definition of actors if you're new to it or still kind of wrapping your head around it. But what I want to show you is really something running. So I've got MiniShift set up on my laptop, and MiniShift is the OpenShift wrapper on top of Kubernetes. One of the reasons I like MiniShift, and I'm working with some other folks as well on this, is that it's often a little bit easier to install than, say, installing Kubernetes on your laptop to play with it. Basically, though, we're running Kubernetes. So one of the things that I've abbreviated it, MiniShift, I just put an alias for MS, is, I can get commands or send it commands, and one of the things is, it's up and running. So I want to start up a console, though. And what this will do is it gives me a nice little web console, which is pretty nice. And I've got these different projects set up in MiniShift. And the one I'm going to show you here is running, I just called it Akka Demo 1 or whatever. But the first thing I want to show you is I want to show you the app that's running here. So I've got one of the things I set up, and I'll show you a little bit about how this was done, but I set up a load balancer. And this is all running on my laptop again, so this is a very elaborate network that's running on my laptop that I have no idea how it's working. Somebody that has more knowledge than I do needs to explain it, but it works. That's all I care about. So once I got this load balancer running, I had got an endpoint to my app. Oops. So this is a visualization of this app. So we're going to be walking through this visualization, and if anybody's looked at, it's a JavaScript. It's implemented in JavaScript. So, and I'll give you the URL to this demo. It's an Akka Java Maven project that has this little UI front end, and we'll walk through what this visualization is. If any of you played a little bit with the D3JS. Anybody heard of that? It's a really cool JavaScript framework. I'm not a front-end guy, but I know enough JavaScript to be dangerous enough to do something like this. And it's a very powerful thing. But what's happening here is we're seeing this system running. So you can kind of see things moving around and so on. And we'll do some more things with it. But it's a visualization of this system that we'll be taking a look at. So what it is that somebody in my company, they nicknamed this thing the crop circle. So I kind of like the name. I don't know if you guys are familiar with crop circles. It's supposedly when UFO, people from other stars come to visit us, and instead of talking to us, they just land in a field and do strange diagrams and leave, supposedly, right? So, but this thing kind of looks like a crop circle. But what I'm trying to represent here is a lot of things. So in Kubernetes, the way Kubernetes works from the perspective of a Java developer, at least my perspective of what's running is, where are my JVMs running? That's all I care about. And bore me with as few details as possible. And this is one of the things I really like about Kubernetes. So in this diagram, there's these three big circles off the center. And they represent the root of a tree of actors that are running inside of a JVM. So there's 3 JVMs running here in a cluster. That's what I'm trying to show in this diagram, okay? And we'll run 3, we'll run 5, we'll run 2, and so on. I'll show you how things kind of change. But in Kubernetes terms, you're running a pod. And a pod runs a container, like a Docker container, and the container runs the JVM. So it's kind of a wrapper. But like I say, all I really care about as a Java developer is where's my JVM running. So in this case, there's 3. Now the circles themselves, what I'm trying to show is some of the things that are running inside of Akka. So the little blue circles are the most interesting on the perimeter. I'm calling them as entity. They're called entity actors. It's kind of a pattern in Akka that is used called cluster sharding. So these entity actors, as you'll see when we go back to it, they're coming and going. And what this demo project is doing is it's generating some internal traffic to kind of simulate traffic coming in, say, from an HTTP endpoint into a microservice. So you can think of this whole system, which is running in a cluster, as a single microservice. All right? These entity actors are handling actions that are being performed against specific entities, like an order or a bank account or an IoT device. So say this is an IoT system, and there's the devices are sending in telemetry. Each device on the back end has its own actor, and it's maintaining maybe some state information about that device, or it's maintaining some state information about an order. Okay, so these entity actors come to life when messages are sent to them to do some work, and they go away when messages stop coming to them, and that's what we're showing in this. Now the next most interesting actors are the green ones, and they're called shards, and this is part of cluster sharding. So you can think of the green ones, in this demo there's 15 of them, it's a fixed number. So what they're used to do is to distribute entity actors across the cluster. And they adapt, as the number of nodes in the cluster change, these shard actors redistribute themselves across the cluster, and we'll see how that works in a bit. And in the big circles, the 3 big circles represent, they kind of represents the pod, but there's also some single actors per JVM that are represented here as well. They're not quite as interesting as the entity actors are the main players. That's where the real business logic happens, and then the shard actors. So the little pink circle that kind of, hopefully it shows, the little circle kind of poofs, that's an entity actor shutting itself down because it's bored. It hasn't received a message for a while, so it shuts itself down. Now, again, what I'm trying to show is that one of these crop circles represents a microservice. So it could be one service in a collection of services. I'm not saying that every service has to be written using Akka or anything. It's just easier for me to create this little diagram. But you can think of this, what we're kind of diving into here, as a single microservice running in a system of microservices. So let's go back to the demo. So we're running along here, and on the console side, we can look at and control the number of pods that are running. So here's the console where it's showing that we've got 3 pods running. And then back in my little crop circle, we can see that there's 3. Now, just as a simulation, one of the things I can do is I set this up. If I click one of these big circles, that's going to send a message into the back end, and it's going to shut down the JVM, which is going to shut down the pod. So now we're down to 2 pods, but what we'll see is those 15 shards redistribute themselves on the remaining 2 pods, 2 JVMs. So the service itself is continuing to run, but now we're constrained back to 2. Now, in the meantime, Kubernetes, and it's happening probably too fast, Kubernetes is going, hey, wait a minute. This service, this deployment should be running with 3 pods. So it nicely goes, hey, here's a new one. So you can see that a third one just popped up. And then Akka is seeing this and going, oh, I've got more capacity. Let me start moving some of my shards over there, which will bring the entities over there. So it's a form of distributing the load. So we're kind of seeing this happen visually where it reacted to a failure. Say the machine or the VM or whatever that one pod was running on failed. Okay, Kubernetes knows how to deal with this, and I kind of call this on the outside. On the outside, Kubernetes is handling running our JVMs. On the inside, Akka is handling running the actors. And Akka knows how to react to JVMs coming and going from the cluster, as well as, and how to distribute actors within the available JVMs inside the cluster. The beautiful thing is where Akka is managing things for us. So say, for example, this microservice gets a spike in traffic. So Kubernetes has this really nice feature where you can auto-scale. So I'm going to just do it manually, but say Kubernetes decides to scale us up to 5 pods. So you can see Kubernetes is going to start up 2 more pods. And those pods are going to spin up. It takes a little bit. I'm not using growl on this yet. But it's spinning up the new containers. They're starting up the Docker containers, and then the JVMs are starting up. The JVMs start up, and in the JVM, my code in the demo app starts up, and it goes, hey, I want to join the cluster. So this is where Akka says, a new node comes into the cluster and goes, hey, I know there's a cluster out here, can I join? So you can see a 4th node just joined, and there's the 5th one. So now we're scaling up to 5. So Kubernetes has done its job, and now Akka sees, I've got extra capacity. I know how to deal with that. It knows how to redistribute the shards. We're still at 15 shards, but we're redistributing the shards, so we're redistributing the load. And Akka is actually kind of doing this. It reacts quickly when things fail, but it's a little bit more gradual when we get more capacity, and we're kind of seeing it happening here real time. What's happening here is this JavaScript client, which is part of this project again, it's just using a WebSocket, and every 5 seconds is doing an update. It's just the way I wrote it. So, but now you can see that we're evenly balanced, where we have 15 shards, we have 5 JVMs running, and the shards have kind of evenly balanced themselves across the 5 pods. If I go back to say the spike is over, and Kubernetes goes, okay, you don't need all that extra capacity, let's scale back down to 3, which we should see pretty quickly is, boom, those guys go away, and then Akka goes, oh, wait a minute, I got those 15 shards, I got to redistribute it, but you can see pretty quickly the shards got redistributed on the remaining 3 nodes. So again, it's this really nice relationship between Kubernetes thinking about things at a more coarse-grained kind of JVM level, and helping us orchestrate at that level, the missing piece that Akka Cluster really needed. Inside of Akka, this is a feature that's been there since like 2013, I think is when Akka Cluster came out, where we could, actors could adapt to changes in the topology of the cluster. So this is really a nice definition or example of what's called a reactive system. The term reactive has gotten really popular lately, We helped develop what, the Reactive Manifesto. If you're not familiar with it, it's a manifesto that's available on the web. Just go to reactivemanifesto.org. But in the manifesto, we talked about reactive programming, but we also talked about reactive systems. And reactive systems are fairly simple. With a reactive system, you're building a system that's always responding, no matter what's going on behind the scenes. So if things are breaking, the system's still responding. If there's a spike in traffic, or the traffic goes up or down, the system is still responsive. So it's really this responsive, resilient, elastic kind of capability that you're looking for in a system. And this is what we're getting now, really, with this combination of Akka and Kubernetes. So as I mentioned, this is just a project, and it's just a Maven project that I set up. It's a simple project, some dependencies, but the thing I wanted to show you in Maven, the two things that were added was the shade plugin, which builds a big jar. It builds a self-contained jar. It's got all my code and then all of its dependencies in a single jar. So like a jar that contains jars. So that's one plugin that was added to the Maven POM. The other one that's really nice as well is that there's here it is, the Docker plugin. And the Docker plugin builds the Docker image. So you do a Maven clean package Docker :build, and it builds a big jar with all its dependencies, takes that jar and puts it into a Docker image, and off you go. And so now we have an image. So it's kind of a simple Maven build that creates this project. There's nothing really spectacular about this project other than it's doing some pretty cool stuff running on Kubernetes. In the main, there's where things are getting started up. I just have this class called Runner. The big thing here is, if you haven't done any Akka coding before, is you create an actor system. And an actor system is kind of like a thread pool on steroids. So it's really this is where Akka starts up and everything gets going. This Akka Cluster Bootstrap is a couple lines of code down here. That this is the code that it takes for when this JVM starts up, it creates an actor system, and then it invokes this Akka Cluster Bootstrap, and it uses that to announce itself to the Kubernetes application and say, hey, I'm here, can I join the cluster? And the magic of joining a cluster and forming a cluster happens in this Akka Cluster Bootstrap. For us as developers, it's just a couple lines of code. And we'll look at this some more, but here's just one example of creating an actor. So an actor it's just a class, and there's different ways you can write actors, but here's one way of creating an actor where you don't call the constructor on it, but you call the actor system actor of, and you give it this what's called props, or like I think of it as properties of the actor. This triggers the actual creation of an instance of the object, but running as an actor in an actor system. Another example here below, another actor is created, and here one of the returns that's coming from the actor of is what's called an actor reference, and the actor reference is the location transparent URL to an actor, basically, an Akka URL. So if I want to send a message to an actor, you use an actor reference. And I'll show you that in a little bit. But this is, there's one class in the main where some things are started up. I'm starting up some actors. These are all actors that I just wrote for this little demo. I'm using some out-of-the-box actors that come with Akka itself to do the cluster, what's called cluster sharding. But it's just an Akka Java Maven project that I'm using here. By the way, minority at Lightbend. I'm at a company with, the gods of Scala work there. Martin Ordesky is the creator of Scala. He's one of the co-founders. And every engineer at the company is there because they love Scala. But I evangelized to the Java community, so I'm kind of a black sheep. So those entity actors, what's happening here is, in the diagram, those blue actors, the entity. So I tried to show in this diagram a little bit of what's going on. So say you're on your phone app, I'm on my phone app, and we're interacting with this system. Maybe we're building an order, okay? As a simple example. So our requests are coming in through a load balancer, typical. And we don't know where our requests, our HTTP requests are going to land in this cluster. And in this example, I've got a cluster of 4 pods. So each pod, each JVM can receive incoming HTTP requests. So the load balancer knows that, that'll, in whatever way it does it, it'll figure out how to send messages. So say you make some kind of, add an item to your cart, okay? And your cart has an ID. And in this simplistic example, say it's ID 64. So your HTTP request comes in to one of the JVMs. That request then is sent as a message to your entity actor. Now there's other actors that are used to actually do the routing that take over the burden. So when in the code that's actually sending the message to the actor, or to the entity actor, you're basically just sending a message. It's like you guys are, you send me a message, and then this is kind of the delegation. My job, I'm not the entity actor, but I'll make sure that message gets to the entity actor. How I do it is my concern, not you as a sender. So I get this message and go, oh, this is for entity 64. I got to figure out where entity 64 is. And it goes, I'll quickly kind of go through this, but it kind of goes through a strategy and actually talks to some other actors and goes, hey, where's 64 at? And it comes back and says, oh, it's on this other pod, the one in the bottom left. So what I do then is I forward the message to my counterpart running on this other JVM and this other pod. So say you're the other actor that gets this message. So you get the message and go, oh, where's 64 at? Oh, 64 is on one of mine, one of the ones that runs in my JVM. What shard does it run in? Oh, it's in shard, I can't see the number, but there's numbers here for each shard. So you know where to forward it. The shard gets it and goes, oh, is the actor for entity 64 around? Is it running? Oh, no, it's not. Let me start it because I got a message for it. So it'll start it up. Now, if you're already running, say previous messages has come in, entity 64 actor is already running. So the message is forwarded. This is what Akka does, and it's got like 6 years of, doing this very, very efficiently. Things like, for example, there's one famous system that we know of at PayPal where they're handling like 1 billion messages a day on I think it's I don't know if it's a 4 or 8 node VMs, 2 cores each. So 1 billion incoming messages a day, and it's, so there's, millions and millions of messages being flown around very quickly. Things like, I think when we run tests, it's like 40 million messages per second per JVM between actors. So this is what Akka does, and it does this very, very quickly. Now, of course, when a message goes over the wire, we're at the mercy of how fast we can transmit messages over the network. But other than that, the latency is, the latency is really if there's a network hop. On the other hand, say I'm interacting with entity 17. I do the same thing. An HTTP request comes in to the same JVM, looks around and goes, where's entity 70 or 17 at? Oh, it's on this machine. It gets forwarded, and so on. So that's basically how things work. And when the number of nodes that are running, the number of JVMs that are running in the cluster changes, all this routing gets handled pretty much instantaneously within like a second or so, because that's how quickly Akka is reacting to nodes, leaving and joining the cluster, especially when they leave. So all this routing and everything is all as a developer, we don't have to really worry about that because there's other actors that we can use that come out with Akka to handle this for us. So let me show you the code for an entity actor. Appropriately named entity actor. Now it's just, just a class. This is the old way. They call it untyped. I haven't had a chance to do this demo in using the new Akka type. The new Akka type is the next release will be fully released. Right now we're calling it production ready, but we're not guaranteed that something might not change. So I kind of held off until it's getting closer, really being fully released. But in any case, this is just a Java class. I'm extending a base class called abstract logging actor, so it gives me the behavior in actor, and it also gives me a quick way to get to do logging. And really, the one method that you have to implement is this one called create receive. So this is where you program the behavior of the actor, and the behavior is when it gets incoming messages, how should those messages be handled? So you can see that there's these match. So for example, match entity message.command class. If it's one of those command messages, I'm going to invoke this command lambda. If it's a query message, I'll invoke another method. So this is just basically how things get into the actor to do something. So the big thing here, if you haven't done any Akka actors before, is that no other code interacts with the code in this actor directly. Nobody calls methods, nobody creates an instance of an object of this thing. You create this as an actor, which I showed you a few minutes ago, and then you send messages to it. That's it. So that's the only way. And actors have a mailbox. So as messages come in, they go in the mailbox, and the actor just takes one message at a time and works on it. So it's like if all you guys sent me messages, all your messages would go into a mailbox, and I'd be kind of chewing through each message as quickly as possible. So the idea is that you're sending me asynchronous messages. My goal is not to block. I get your message, I do my work, and I'm done. And maybe I send you a response back or not. That depends on how you and I designed the code to deal with this. Just real quick, when I get a command, this is just a simulation. I'm not doing anything with it other than kind of logging it. So there's some interesting logging that occurs. And the thing I want to show you is that I'm sending an acknowledgement message back to whoever sent me the command message. So again, this is by design by me. It's not a requirement of Akka. Akka just says how can you receive messages and how can you send messages. So I inherited this method called sender, which is whoever sent me the message. I call the tell method, which is the method for sending a message. I build an object, this command Akka, and then on the end here I say, this is who sent it. So I'm kind of building an envelope, basically, or a message where it's got the to, the from, and the contents, basically. That's pretty much it. So again, there's this really nice relationship between what's happening inside the actor system. Like here I'm showing that example where we're down to one pod, one JVM running in one Docker container, running in one Kubernetes pod. And say Kubernetes decides to give us 2 more pods, so we scale up. And then Akka reacts to that because of the way I set this demo up so that it distributes the work around those pods. And when we lose a pod, it's, Kubernetes, will say, like we saw, that, oh, I lost a pod, let me replace it. And Akka is going, oh, I lost a node in the Akka cluster, let me deal with that at the actor level. So it's this kind of, on the outside, Kubernetes is running our JVMs. On the inside, Akka is handling the things that it can do inside the JVMs. And those shards, this is just a strategy for distributing work. So I'm showing here that we're running on 4 pods, and one of the pods goes away, so those 3 shards need to find a new home in the cluster. And that's what happens. So there's a kind of a cool feature that I like to show people about actors and how you can do like this intra-cluster messaging. And so the term is cluster aware. So the idea is that, and this is by design, say we're developers and we design this and we go, we need an actor per node in the cluster that knows how to talk to each other. So we know that there's that situation, that there's an instance of this actor, one instance running on every node in the cluster. And with that knowledge, it's fairly easy to write the code to do some form of messaging. So it's these kind of cluster-aware actors where one actor knows that it can send messages to the other actors, the same actors running on other nodes. And in this demo where I used this was building this tree that's being sent to the GUI, to the front end. So the fun thing here is that in this example, say there's an actor. When the dark blue circles represent actors that have just started. So when an actor just starts, one of the first things it does, it sends a message to another actor and it says, hey, I'm here, add me to the tree. And this is a tree thing that something I did in my code. Well, what it does is it sends a message to another actor. There's a single actor per node that's building the tree. When that actor gets it, because, okay, now I know to update my tree, but I need to notify my compatriots across the cluster. So what it does is it forwards that message to its counterparts across the cluster. So the tree is being built in every node in the cluster, effectively. Because I don't know where my browser is going to hit. So I want to have the same view of the tree regardless of where the HTTP request comes in from my browser. So this was a trick to do it. Now, imagine trying to do this on your own. We're talking about doing things across the network. We need to know about what nodes are running in the cluster, all these types of things. The code to actually do this is pretty trivial. So back in the entity actor, one of the things I do is that when I know that the actor's just started up, I invoke this method called notify start, just something I wrote. And in notify start, I create an action message. And this action message, what I do is I send it to an actor that I have the actor reference called, and I call it HTTP server. So there's another actor that receives this message. So the entity actor is done. It started up, it built the message, and it fired off to another actor that it knows about. Entity actor is done. If we go to the HTTP server actor, go up to where it receives messages in the create received method. So here's where that incoming message comes in, action. And so I invoke this method I called action entity. Action entity gets that message, logs it out, and then it looks at the contents of the message. And this is something I just set up again. If it contains the action start, then it's going to add the entity to the tree. If it contains the action stop, it's going to remove the entity from the tree. But then, if the message says, hey, forward me, it's a little flag in the message, then it's going to invoke this method called forward action. So forward action, this is where the fun begins. In forward action, I go into a loop on the nodes in the cluster. And that's done with some Akka objects that I can get a hold of. So there's this cluster object that I got from the actor system. And then I get a list of the members, and for each member in the list, I loop through it. And I just take a quick look at the member. If it's not if it's not the node that I'm running in, if it's not myself, and that other node is up, so I can check, is that other node up? Because they have state. It could be up, it could be starting, it could be stopping, it could be, something. And everything's good, then I'll invoke this method called forward action, which is down here. And forward action, basically what I'm doing is building a actor URL. And I'm taking the member name and the path to the actor, which is my path. I'm kind of building a actor URL, which is called an actor selection. And then I'm doing a tell. So in this loop, this was the code, these two methods, to loop through all the other members in the cluster and forward the message to them. So an entity actor started on my node, I got the message, I updated my tree, and then I sent the same message to my counterparts across the cluster. They get the message. Now when they get the message, when I send the message to them, I turned off that forward flag. But this is just by my design. It's not anything Akka happened to do. But in any case, the end result is, we're getting this ability to do something like this, which is, easily sending messages across the network, with, about 10 lines of code. So I did that. So there's also the concept of a cluster singleton, just real quick. Cluster singleton is a single instance of an actor that is only depending, there'll only be one no matter how many nodes are in the cluster. So if the node that actor is running on goes away, the singleton actor will be started somewhere else. This is sometimes used, and I've used it in some projects. I have some example projects I'll show at the end of the talk, where you need to make a kind of a cluster-wide decision. And you want to make it so that there doesn't have to be an agreement or anything like that. It's like you delegate the work to the singleton. Hey, singleton, make a decision for me. So you send a message to the singleton, and the singleton sends a message back saying, here's the result of my decision. And that comes into this demo that I've been running is called Cluster Sharding. And the idea is that when you need to send a message to an entity actor, you send it to a local shard region actor, and that's the actor that handled all the routing that I talked about earlier. And this is kind of leading into doing event sourcing and command query responsibility segregation, which I think there's a talk coming up right after mine that I want to sit in on. Anyways, the entity actors are ideal for handling events coming in. A command comes into the actor, which is a request to do something. It's something that hasn't happened yet. Please add this item to my shopping cart. When the item is added to the shopping cart, that event is persisted in like an event store, and then the state of the entity is updated. It's changed. So the shopping cart now contains, say, a new item in the shopping cart. So what the entity actor is doing is it's handling these commands coming in. It's validating those commands are okay, and then it's committing or persisting those events to some kind of event store, and then updating its state. So in effect, those actors are also a little form of a cache. Event sourcing, anybody doing event sourcing in CQRS? How many have heard of it? Okay, it's really, really interesting. If you're getting into microservices and you want to break apart your database, because maybe that's a battle that you're fighting, and that's a lot of battles that I know a lot of people are fighting, you're breaking apart the monolith at the code level, but you haven't broken apart the monolith at the database level. This is a nice pattern to try and introduce. So this is really where this is all leading. The cluster sharding is just kind of a stepping stone to doing more interesting things like event sourcing in CQRS in a single microservice running in a cluster of JVMs. So this is why Akka really loves Kubernetes. It's the orchestration platform that it's been waiting for. I think we were kind of a little ahead of ourselves when Akka came out, where we had all this marvelous capability of doing things in a cluster of JVMs, but we were leaving the management of the cluster JVMs to something else. And now that gap has been really closed with something like Kubernetes, which is very exciting. So this project that I've showed you is available, and I post these slides, but this project is the first one. It's on my own GitHub, and it's just called Akka Java Cluster OpenShift. And then there's a series of other projects that kind of led up to this project. So the intent is you can grab these, clone them down to your machine, build them, and play with them. And it'll run a cluster. So it's got all the ingredients that are needed to run a simple cluster, including the configuration file. This was one of the things that kind of annoyed me when I was playing around, is when I grabbed something to play with, some other project, it seemed like it was fun to get it working. Here I try to make it as simple as possible. So I've been working a lot on the READMEs. I'm really bad at that, so people have been beating on me on the READMEs. So the READMEs are really good, and I'm going to be working a lot on the OpenShift one, but there's sufficient documentation in there to do it, including the visualization. So I know other people have taken this project and used it, because the visualization is such a powerful way to show people what's happening and kind of explain, yeah, see this little circle here, this is what it's doing. And instead of just kind of, before I'd be waving my arms around going, there's this cluster thing, and it's really cool, and people are looking at me, what the heck is he talking about? The visualization, I think, is a lot more powerful. So if you want to kind of take something and demo it to yourself, and maybe demo it to your colleagues, that's the intent. The other projects don't have the GUI front end yet. I was thinking about doing it, but I'm a fanatic about logging. So I tried to make the logging very readable, where you can see what's happening in the cluster as nodes come and join and leave the cluster, and how the cluster forms. There's logging that shows that pretty clearly, and it's also showing some of the activities that are going on with these things. But each project, the first one is a very dead simple, like one single actor project, and it progressively builds up to this OpenShift one. I've also written a little O'Reilly booklet. If you're interested in just kind of learning about actors without any code, but just kind of actor think. It's a quick read, lots of pictures. It's free to download. And I thank you very much. We got just under 2 minutes for any questions, if anybody has a question. And I'll be around today. I have to leave tomorrow, but I'll be around today. All right, thanks.